chapter 20. So chapter 20 is so we've kind of been working on the cardiovascular system. Blood obviously kicks it all off. And then the heart, and then of course, chapter 21 is going to be blood vessels, and that kind of creates the big triumvirate of the cardiovascular system. And so this is the heart section. There's a lot of really, really important stuff in this chapter. Every chapter, few chapters or so, if you want to look at any kind of course curriculum for any class, generally there's what I call the bullseye chapters. These are the ones that are like the heart and soul of that class. Like if you don't really get these chapters down, that's kind of like the centerpiece of the class. For this class, that centerpiece is these three chapters. It's the heart chapters, right? So that's the reason why this one tends to be fairly full, because it is the epicenter of A&P, and especially of human physiology. And to a lesser extent, the next chapter. So from after this chapter on, this chapter will feel like it's long. You will feel like you're in the cardiovascular system forever. That's because it's true. But that's for a reason, because there's a lot going on there. And then it makes the chapters coming up much, much easier and much faster to go through because we have a good firm foundation in the cardiovascular system. Okay. So let's go ahead and start off, first of all, with our structure, right? So we're going to be taking a look at some anatomy. And a lot of this you can also see, and you have seen in your sheet parts. But if you recall, back in A&P1, we talked about the different types of membranes, right? So we talked about cutaneous membrane, we talked about serous membranes, we talked about things of that nature. And the serous membranes, we talked about having two different pieces. It actually has a pretty traditional structure, right? If you recall, I don't know how well you guys hit this in A&P1, but it's an area that's noteworthy in A&P1, right? So the basic structure goes something like this. The serous membrane system is designed to cover the cavities, right? It's cavity associated and the organs associated with those cavities. And so the way it goes is that the cavity, the wall of the cavity, if you will, is essentially lined on the inside with a liner. That's called the parietal layer, right? So that's the outermost layer. And then there's like a bit of a space, the cavity itself. And that's kind of that's typical for all serous systems. And we'll see this recapitulated actually throughout the semester. And then the second liner, which is the visceral liner, is the lining that lays right on top of the organ itself. Okay, so you have this kind of three-part system: visceral layer, space, parietal layer that kind of covers the inside wall. And we see that same pattern here because when you take a look at the pericardium, this is a serous membrane system. And so that's what they're talking about when they're talking about a double lining, right? They're talking about the parietal layer and the visceral layer. So as you start from inside going out, we're going to start off with that visceral layer. So this is the area, the innermost part of what they call the pericardium. And so this is that inner liner. That rests on the actual heart muscle itself. And we're going to take a look here at a little peculiarity associated with the pericardium itself, but this is the innermost layer. Then as you go beyond the visceral layer, you're going to hit the cavity area, the open space, and then you're going to run into the next layer, which is going to be the parietal layer. This is the outer layer. And it forms the inside of what we call the pericardial sac. A lot of you guys saw this in your cats, right? So when you're kind of in there fishing around the blood vessels, it looked like a little sandwich bag wrapped around the heart. So a lot of you guys saw this. That's the pericardial sac, and that's the innermost layer. On the other side of that is going to be the parietal pericardium. And so this layer piece of it is important, right? Because when you create this sort of gap, right, so the visceral gap and then the parietal, then what you have is in between the pericardial cavity. And this almost always, usually this cavity, with very few exceptions, will contain some sort of a fluid. In this particular case, it's pericardial. And that's kind of important, right? Because fluid has pressure. The heart is basically beating inside that little sac. And so you can imagine that the more fluid is there, the more pressure it's going to exert. That's going to have direct effects on the actual heart and the work that the heart is trying to do, right? As a matter of fact, this is pericarditis is an inflammation of this sac where you start to accumulate excess fluid in this little sac, and it kind of starts to cause some pressure problems. So the sac itself, as you might expect, is actually connective tissue. So it's going to be a connective tissue sac that kind of wraps around the heart itself. And this is kind of what it looks like. So just to kind of refresh your memory on what we're talking about here, because a lot of times it gets very abstract and all you're just doing is talking about pericardial cavities and pericardium and all that sort of stuff. But this is what it looks like. For our purposes, you have 2, maybe 3 dominant cavities that we're going to be working in for the most part. The thoracic cavity, which is broken up into subcavities. So you can carve up each side into the 2 pleural cavities. So this is basically where you house your lungs. So they have their own kind of section, if you will, subdivision of the thoracic cavity. And then the centerpiece is the mediastinum. Now, at the bottom of the mediastinum is a specific chamber that's special. This is the pericardial cavity. So the heart actually rests at the bottom end in the mediastinum of the thoracic cavity. So it's kind of at the bottom of the thoracic cavity. And then, of course, this one here is the abdominopelvic, if you want to toss pelvic in there, cavity. Okay. So the pelvic cavity proper basically being all the space that's inside the bowl that's created by your hip girdle. So that would be that kind of pelvic proper. A lot of times we sort of run those two together because there's not like a separation the way there is with the thoracic and the abdominal between abdominal pelvic. It's just largely you sort of fall into this bowl-like area where you are in the hips, basically. So around this then, and around the heart in this pericardial cavity is going to be your little pericardial sac with your heart in it. Okay, so that's basically an important piece. So it's a slight modification of our traditional serous system, but it's basically the same idea. And this is kind of what it looks like from the top down when you're sort of looking down from above, a superior aspect of it. So you can see here is your 2 pleural cavities here with your lungs in them. You can see this is going to be the upper portion of your mediastinum. Now, what happens is the upper portion of your mediastinum is largely your trachea and your esophagus going down. So here you can see your esophagus right here. And then the trachea has already split, so you can see the 2 branches of the 2 mains going into each lung. So we're beyond that split where the trachea splits into right and left main at this particular juncture. But you can see that what happens is the pericardial cavity inhabits the anterior portion of the mediastinum while the trachea goes behind the esophagus goes behind in the posterior region of the mediastinum. So this is kind of important so for positional purposes, because this also allows you to be able to see the nature of the sac. So for instance, here you can see your pericardial cavity, which is going to be this whole space right here. And then the outermost layer is going to be the pericardial sac, of which the innermost layer is the parietal pericardium. And then the layer that's resting right on top of the heart is going to be the epicardium. So you can actually see these really well right in here. So here's your visceral layer, your pericardial cavity, and then your parietal layer, which is bundled into the rest of the connective tissue of the pericardial sac. Okay. And that's not an uncommon feature. Your parietal layer is designed to sort of adhere to the cavity wall. So it's not unusual to find the parietal cavity is sort of complexed with the connective tissue structure of a wall or a cavity or something like that. And so what this basically does is it kind of gives you anchorage. But if you notice over here in this particular area here, you notice how the two membranes are actually interconnected with each other. So basically by tethering this parietal pericardium to your pericardial wall, you're able to actually tether the entire thing. So it's connected up here and continuous with each other. Okay. So a lot of times this is a little spatially confusing for students. They're like, okay, wait a minute. First of all, I never did get that whole serous lining thing back in AMP1. It doesn't make sense to me that you would have multiple layers and stuff like that. So how do you get that? It's very simple. Just imagine the balloon analogy. The way you create any kind of serous liner, right, with that kind of visceral cavity parietal pattern to it, is simply like putting your fist in a balloon, right? When you put your fist in that balloon, the layer that's resting on top of your fist is going to be the visceral layer. That's that innermost layer. Then there's like a little airspace, right? Because you're not collapsing, you're not letting the air out. So there's a little bit of airspace. So that would basically be the cavity, right? So that's your cavity of any kind of a serous system. And then of course you've got the outside region, which would be your parietal region. That's the part that's attached to the wall. Okay, and the same basic structure happens here. So here you can see you basically stuck your heart into the balloon, so to speak. And here you can see your epicardium or your visceral pericardium. You see your space here, and then you see your parietal pericardium. So a couple of things to point out, first of all, with the heart is when you kind of take a look at the parietal. So we said that this is associated with connective tissue, and this is worth kind of taking a look at. So here you have the cavity. And then typically speaking, you see this kind of pattern very commonly, which is the reason why I like to stop and sort of point it out and highlight it, because you see the same structure over and over and over again in various organs and in various systems and scenarios, but it's the same basic idea. So when you have your parietal pericardium, the first thing you have on the inside is going to be mesothelium, which is simple squamous typically, right? One layer, flat cells. That's typically what it is. But we all know that whenever you do a simple squamous layer or any kind of a squamous layer, that you can't just, it's not just free floating, right? You have to actually tether it or stick it, if you will, to a foundation, right? You always have to have an underlayment associated with epithelial tissue because it inherently doesn't have anywhere to stick. So you have to lay down the underlayment first and then stick the epithelial cells on the underlayment. Remember, that's how we talked about the basement membrane when we're talking about epithelial liners in AMP1, right? That the basement layer represented sort of an underlayment on which you actually glued or stuck or tacked on your epithelial cells. Well, when you need extra structure, then you build on that theme. And instead of just leaving it up to the basement membrane, you can also add connective tissue in order to give more robust structure to that epithelial layer. That's exactly what you're seeing here. So in this particular case, because the heart is a moving organ, so there's going to be some mechanical stress and wear and tear on these tissues, you want a little extra oomph to the structure, right? So you need a little more robustness. And so that's the reason why you're adding connective tissue here. And so the first thing you do is you basically put in some areolar tissue. Now remember, this is loose connective tissue. And if you're in my class, I always refer to areolar tissue as loose fill, right? It's kind of the stuff that you use when you need to fill a gap just with stuff, but you don't need like a super ton of structure in there. So it's great just space filler is what it is. And that's what loose areolar connective tissue does for you. If you want something more robust structurally, you have also another type of loose fill. So dense irregular, your skin tissue, the dermis tissue is more robust, structurally robust. So that's kind of like a filler, but it's a more robust filler. So it gives you more structural integrity in that sense. But in this case, you're not talking about, the rough treatment that your skin gets. So you don't need dense irregular. It's overkill, right? You don't need that type of support. So loose fill areolar is perfect for that purpose. And so you add a little bit of areolar in there. And then, of course, you have to that the fibrous fibers, mostly collagenous, probably some elastic fibers as well, associated with the actual pericardial sac. Now, one thing to always remember, if you didn't pick this up in A&P1, you should pick it up now, is that the way connective tissues work is they work like Legos. So if you've got connective tissue, you can always wire yourself to other connective tissue. That's the beauty about connective tissue, right? They're interlocking. And so one of the reasons why you have areolar tissue is because you already have connective tissue. And if you recall seeing the histology slides for areolar tissue in A&P1, you notice it's got all kinds of fibers all over the place, right? And so if you've got those fibers, then what you can do is you can weave the fibers of one connective tissue together with the other. And so that kind of weaving is exactly how you connect connective tissues to each other. And we see that a lot. And that's one of the reasons why it's important that on the outside of the sac, which is the one that's facing the inner wall of the pericardial cavity, it's important that that's connective tissue. Why? Because the inner wall of the pericardial cavity is also going to be a lot of connective tissue in there, which means that gives you the ability to weave those two structures together and stabilize the sac. So it's not just sort of flopping around in space. It gives you a little bit of structural anchorage, right? Always remember that. You can always unite two connective tissues by weaving together their collagenous or elastic fibers. That's a common strategy you see in A&P. That's how you attach tendons to your bones and so forth. Okay. And it becomes useful here. Why? Because here we already have our sac doing just that. So down here in the bottom, oftentimes at the apex of the heart, which is oftentimes overlooked, notice this big sheet. What is that? That's the tendon of the diaphragm. So you're taking essentially this collagenous pericardial sac and you're weaving it together with the tendon of the diaphragm so that it's anchoring the bottom or the apex of the heart and tethering it to a strong substrate. Remember, a lot of you guys have been working with the diaphragm and cats, kind of moving it around. It's a large muscle. It's a bell-shaped muscle, so there's a lot of tendinous material there holding it together, and you have your heart tethered to the bottom of that. So that's an important aspect of the structure of the heart itself. So let's take a look at the layering of the heart. Now, one of the things to understand is that when you take a look at the heart itself, there's three major layers. So there's the epicardium, which is the outermost layer. Of the heart. Then, of course, the myocardium, which is the dominant layer. And then the endocardium is the inner lining. And we'll take a look at these guys here in just a second. So with the epicardium, that epi means upon, cardium, of course, the heart. This basically means it's resting on top of the actual heart itself. However, the epicardium is essentially exactly the same as the visceral pericardium. That's not true for any other organ. Like, for instance, if you were to look at the visceral peritoneum that's wrapped around the stomach, it is a different, functionally separate liner from the stomach tissue. They're not synonymous. It's only in the heart that you see this visceral liner being essentially synonymous and this exactly the same thing as epicardium. Okay. So the epicardium is generally the visceral pericardium. And this is the layer that covers the outside of the heart. Now, the myocardium is your muscular wall. So this basically has all of your cardiac muscle cells. This is the contractive or the contractile layer. So when you're talking about your heart contracting and pumping blood, this is the one that does it. It says it in the name, myo, right? So this is muscle. This is muscle of the heart. So these are the guys who will basically contract in order to actually squeeze the blood out of the chambers and around your body. So the atria has myocardia, and it wraps around the atria and also around the great vessels like the aorta and the pulmonary trunk. And then, of course, the ventricular myocardium is also wrapped around the right and left ventricles as well. We'll take a look at that. They actually kind of drape around the ventricles, kind of like a toga, kind of like the folds of a toga. We'll see that here in just a second. And then, of course, the endocardium is very simple. It's basically simple squamous epithelium, right? This is very simple inner liner. So notice a theme here. Whenever you're cavity facing, or you're facing kind of a finished area, kind of like the inside of a ventricular cavity, or the inside of the pericardial sac, or the inside of any type of an organ, notice that has a very common structure, doesn't it? That simple squamous endothelium. It's a very common structure that you see throughout. It's kind of like, think of it this way. It's kind of like all the connective tissue of these layers is sort of like the walls, right? We're going to go back to walls again, right? We all know that inside the walls is going to be all sorts of technical stuff, right? There's going to be electrical in there. There's going to be plumbing in there. There's going to be all sorts of pipes and stuff, right? And so we don't see that, do we? Could we? Sure, we could. Is there any reason to hide them? Not really. Functionally, there's no reason at all. So why do they cover them up? To give us a finished surface, right? I mean, because our functional activities in here don't require that. And so it's to give them a functional surface. So we have a very thin veneer of wall between us and the electrical and the plumbing. It's literally just a few inches away, right? So the drywall system and, you know, either the paint or the wallpaper system, that represents the endothelial layer of most of these structures, okay? And that's kind of what the endocardium is like. And so here's a good example of it. This is kind of what I like this one because it basically goes all the way from the outside down into the inside. So if we take a look at our parietal pericardium first, you can see here's your connective tissue piece right there. And then as you start to move in, you get your areolar, that's your loose fill, and then your endothelial, simple squamous mesothelium cells. Notice that it's just a smooth lining, just like a layer of wallpaper on the inside of a finished wall, okay? Then you're gonna have your pericardial cavity here. And so that'll be filled with fluid. And then as you start to go down, so that's your parietal pericardium, your pericardial cavity. And now you're going to get down to the epicardium, or better known as the visceral pericardium. And so here you can see there's another kind of a similar structure, similar sort of thing going on here, right? Notice we have the mesothelium in this layer right there. That's simple squamous, just like you had with the parietal layer. And then underneath that, what do you have? Loose fill, right? An extension of your connective tissue foundation. So you actually add a little bit of areolar tissue just underneath it to give it a little bit of a soft, not robust, not very hard, but a soft sort of an underlayment or a filament. And then you have, in here, you have the majority of your cardiac muscle cells. So this whole section right here is going to be your cardiac muscle cells of different sorts. And then on the inside, you're going to have the endocardium system. Now notice you kind of reverse it, right? So you use your loose fill, again, your areolar tissue, to give you a little bit of structure. By the way, that's also helpful. Why? Because, well, if the myocardial cells are busy contracting so that you can pump blood through your heart, you probably don't want an endothelial liner attached to it, because its job isn't to hang on to your endothelial liner. It's got to contract, right? It's got better things to do. So it's better to have this little connective tissue areolar patch right there so that you can glue your endothelial cells, simple squamous again, to that areolar pad. And then, of course, on the inside here is going to be the lumen of the heart. Lumen just basically means the inside of something. Okay. So that's a nice little image, because basically it takes you from the outermost and then stepwise just walks you all the way through to the inside layer of the heart itself. So let's take a look at the way the musculature, especially the myocardium, is arranged. You can see that it's basically arranged in these sort of folds of muscle that basically kind of wrap around the ventricles, and they kind of wrap around like this. And you can kind of see how they're wrapped around the atria as well, kind of like a toga sort of wrapped around somebody, where the folds are kind of draping from one shoulder to the bottom hip of the opposite side. And so it's a similar sort of a structure, but notice you're basically wrapping that around the entire ventricular system. And that's what you guys were cutting into. When you were cutting in the sheep hearts and you saw that big, thick ventricular septum, that's what you were cutting into, was the folds of the myocardia as they were kind of wrapping around the heart. Okay, this section is a little bit of a review from AMP1, so I'm going to move quickly through it because you kind of got this when we studied muscles. But when you take a look at cardiac muscle tissue, it stands out from the other two, smooth and skeletal, in the fact that it's got intercalated discs. Now, intercalated discs are essentially the junctions of two muscle cells. So this is the interconnection between two cardiac muscle cells fastened together with desmosomes. So if you took general bio, you will recognize desmosomes as one of the cell connections that we study in general bio. But it also has, and this is also important, what's called gap junctions. Now, gap junctions, essentially, it's a type of cell junction. But what a gap junction basically is when two cells are joined together in association with each other by these little open channels. So what that means is that they are basically interconnected to each other. So when something changes in the cytoplasm of cell number one, it immediately goes through these gap junctions and is communicated to cell number two. So what does that mean? That means that these two cells have the capacity to essentially respond. Sorry, that's my OCD coming out right there. They have the ability to respond simultaneously in unison. Think about it. The task of a heart, the heart muscle, is different than it is for skeletal muscle, right? Your skeletal muscles are not contracting in unison. Your skeletal muscle fibers are contracting in waves. They rotate, right? Kind of like pitchers rotating games. Your muscle, your skeletal muscles rotate as you're holding a load for long periods of time. Same thing with your smooth muscles. They're not in unison. They're basically, they're kind of rotating, but they're basically contracting to give you sustained, long-term, enduring tension as well. It's only the heart muscle that contracts in unison. So the task of the heart muscle isn't to just contract, but it's to basically contract in such a way that you can essentially take a heart full of blood and then squeeze it in unison and then eject that blood out to the rest of the body. Now, in order to do that, that means every single heart cell, every cardiomyocyte in the heart has to contract at the same time. They all have to squeeze at the same time in order to get the maximum force necessary to get the blood out to the body. especially if you're big like us, where you have to get blood out to the tips of your fingers and the tips of your toes, right? So that's a lot. That means you have to either contract all at once and relax all at once. That means everybody's got to be listening to the same instruction at the same time. How do they do that? Through gap junctions. It's the primary way that they're able to coordinate that type of uniformity across the board. So when they get an instruction to contract, everybody gets the instruction to contract, and they're all able to contract at the same time. So this is your cardiac muscle cell. You can see that it basically is a single nucleate. It's got lots of mitochondria, as you'd expect. The boundary of an intercalated disc is basically where one cell stops and the other begins. And this is where you're going to find your gap junctions. And then, of course, they're also cross-branched as well from one cell to the next. This doesn't really show it very well, but unlike other muscle types, which are like, for instance, skeletals, just long cylinders of muscle fibers, in cardiac muscle cells, they're interconnected. So when you pull a cardiac muscle cell apart, it's kind of like a fishnet. It's like interconnected with each other. Okay, and so that's important because that basically means they're able to get maximum communication with each other. Okay, now let's take a look then at the inside of the heart. So we're taking a look at the heart in general, at some basics, but now let's go ahead and start cutting this thing open and see what we got inside there. So the first thing we're going to see is a couple of septa. So a septum is basically a Latin term for wall. So it's a muscle wall is what it is, and it separates the two atria. So you'll have the two atria like this. You'll have a septum in the middle. It's like that. And then you also have an interventricular septum, which will separate the two ventricles. Like that. So here's your two septa. So this would be number one, and this guy right here would be number two. Okay, so that's separating your two chambers, and that because of the septum, the septa, or plural, then this creates your four-chambered heart. Now, not everybody has a four-chambered heart, right? So amphibians have a three-chambered heart. Different organisms have some have a two-chambered heart. So there's different types of hearts out there. And mammals happen to have a four-chambered heart. And we separate our activities, by the way, by the septation. So what we do is we separate it into right and left halves. So in the left side, this is the systemic circulation. And on the right side, this is the pulmonary circulation. Now, a couple of things associated with the right side. Obviously, you have the right atrium, you have the right ventricle, but you also have a couple of valves in addition to that, separating the right atrium and the ventricles themselves. So the septa are separating the chambers. That's separating the heart from right to left, right? But now to separate the atria from the ventricles, you have a series of valves. And you have, first of all, the set of valves we have is what's called the atrio for the atrium, ventricular for ventricle valves. The AV valves, you have two of them. And so basically these guys will connect one ventricle to the atrium. So for instance, your right atrium is connected to your right ventricle by way of the right AV valve. And you're going to see that right about here. So that's your AV valve. And then typically speaking, you have a situation here now that allows you to have one-way blood flow. So it basically prevents backflow. As it moves from atria to ventricles. And the other thing also that you notice is that these guys look like basketball hoops, right, with a basketball net that's tethered by muscular swellings inside the ventricle called papillary muscles. So you have two AV valves on either side. So this is the papillary muscle. This is the left AV valve, also called the bicuspid or the mitral valve. All those are synonymous. Actually, in clinic, you won't hear usually left AV valve. You won't hear bicuspid. You won't hear bicuspid. You'll oftentimes hear mitral valve. So most of the cardiologists I worked with, they talked about the mitral valve, not the bicuspid. And it's simply called bicuspid because it has 3 flaps. And we'll see an image of this. It's a really, really nice image of this that shows you that. And then, of course, the same thing is also true over here, only in this case, you have the right AV valve or the tricuspid. That has 3 flaps of connective tissue that makes up this valve. So this is how you regulate flow of blood going through the AV valve from the atria into the ventricle. And that's kind of an important piece. Now, from the right atrium, the question is, how do you get blood there? Well, let's take a look at this here for a second. So this is the arrival. So these are veins. These are some of the great vessels. And we'll also look at the left side as well of the great vessels that are wired to the heart. The first one is obviously the superior vena cava. This is basically taking blood from your head, neck, and upper limbs and chest. So for instance, all the blood coming through your jugular veins, which a lot of you guys saw with your cats, right? So as the brachiocephalic vein makes that split to subclavian, the other part goes jugular and it goes up the neck. Well, that's where the blood is coming down from your brain that's already been spent and used, and that's going down into the superior vena cava. So you remember the venous flow is going toward the heart. And so that blood is moving in and heading toward the superior vena cava and also from your shoulders. So when you're looking at the subclavian, that's blood coming from your shoulders and heading to your heart. And when you're looking at the jugular, that's coming from your head and moving toward your heart as well. From your lower trunk, it's coming through the inferior vena cava. So all the blood in your legs, your digestive system, so all the nutrients you absorb in your bloodstream through your intestines, all those mesenteries, a lot of you guys saw the mesenteric arteries, right? So all those like little itty bitty red arteries that were kind of wrapped around the small intestines of the cat. Well, there's veins that basically mirror those, that are right next to those, the mesenteric veins. And so what those guys are doing is those guys are absorbing all the nutrients from what you've just eaten and is taking that blood to the liver for processing. And the liver does its magic on it, sort of make sure it's okay, metabolizes what it needs to. And then a lot of you guys saw in your cat the upper portion of the inferior vena cava as it leaves the liver on its way to the heart. And so that's carrying the blood that has already been sort of screened, if you will, by the liver. And now it's going to be moving up into the right atrium. So blood is coming into the right atrium from above through the superior vena cava, from below through the inferior vena cava. And then the last one, and probably the biggest one, is the coronary sinus. So a sinus is basically a swelling area where blood pools. An open chamber. It's an open area. That's generally what a sinus is. So think about your own nasal sinuses. It's an open area where fluid builds up. And we all love that because it gives us a headache, right? From the pressure. But a sinus is all the same. The coronary sinus just happens to be a vascular sinus where blood pools before it goes into the right atrium. It's kind of like a collecting place. It's like a meeting place. Hey guys, let's all meet at the coronary sinus before we head on into the right atrium, right? So it's kind of like you're meeting your friends at Confluence before you go kayaking or something like that, right? So that's the coronary sinuses from, and it's basically going to be draining blood from these cardiac veins, which are part of the coronary system. Or the coronary system isn't arteries and veins from the heart. It's to the heart. This is the heart's nourishment, right? Remember, the heart is a muscle, so it needs to feed. It needs nutrients and oxygen too. And so the coronary system that we saw, and we kind of talked a little bit about that in lab, this is basically where you kind of drain that back into the right atrium. So you have those major openings in the right atrium. There's also another one at birth, fetal development. Basically, that's called the foramen ovale, not to be confused with the one in your head. Some of you remember that one, right? That's not the same thing. Basically, is before birth, a lot of times people don't realize this, we're actually a three-chambered heart. So our atria look something like this. There's like a little opening there. So basically what that means is the atrial blood mixes together. And that's for a reason, because mostly if you take a look at the blood flow pattern in a fetal heart, it's largely centered around systemic flow, right? So when the heart is beating in a baby that hasn't been born yet, it's hard because it's only three chambers, because the two atria are open to each other through this foramen. It's basically acting like a three-chambered heart, but it's focused more on systemic delivery. Why not pulmonary? Because you don't need it, because mom's doing the work for you, right? So she's the one who's breathing for you. You're getting oxygen in from her. So it's kind of a waste for you to actually start up your pulmonary side until you need it, right? This is one of the reasons why one of the last systems to develop in fetal development is the lungs, is because mom's doing all the heavy lifting for us. And so we don't really need them until we need them. And that's when we take our first breath, right? Which is probably one of the most shocking things we've ever experienced, if we could ever remember it. Think about it. You're breathing fluid for most of your life, and then all of a sudden you start breathing air. It's probably about as shocking and disturbing to a baby who's newborn as it is for us to dive into a pool and start breathing the water. That's probably the reason why babies are crying all the time when they come out. They're like, wait a minute, it was nice in there, it was warm, the lights were low, I was sleeping. Right now I'm breathing air. What is this going on? I'm like drowning in air now, right? So that's basically what happens. So normally then at birth, automatically this seals up, and it causes what's called the fossa ovalis. Now it's supposed to seal up, but what happens if it doesn't? It causes what's called ASD, atrial septal defect. And it's not necessarily lethal. It can be. It's not necessarily lethal. There's actually people walking around just fine with ASD, because ASD is quite variable, right? In some cases, if the hole is really large, then you've got you got to deal with that, right? You can't live. Our body cannot have appropriate distribution of oxygen and nutrients with a three-chambered heart, right? The demands are just too much. So you need to fix that if it's a gigantic hole. But a lot of people are walking around with a fairly smallish hole, varying of severities of atrial septal defect. And for the most part, it doesn't really bother them. Somebody like this would probably have to have, you couldn't be an athlete, right? Because at normal speed, like for most of us, it's fine for our demands. But if you were to try to high performance yourself up and try to be an athlete, it would probably strain your cardiovascular system, and it couldn't give you what you needed, and it would probably create a lot of strain on your heart, and it could be lethal, right? So this is kind of one of those things that would basically be like, yeah, you know what? At normal speed, you're fine. Just don't train, because if you train, it could kill you, right? So yeah, we actually had quite a few patients that had atrial septal defect. It's not necessarily super uncommon. Some do, some don't. Like some will report just kind of like overall, kind of lethargy and like during their normal cardiovascular screening once they get to that particular age routine. They'll do like a standard echo and the cardiologist can pick it up just like that. A lot of people that's how they find out about it for the first time. And they're for the most part, they're living with it. Others complain because it's like they try to get active and they realize that they can't do it because it's like they're breathy and they're showing symptoms of stress, cardiovascular stress when they exercise, and that's the symptomology that brings them in. And then they take a look at it and they realize, oh yeah, you've got ASD, or something of that nature. So some people do and some people don't. So it depends. If you do something, it's possible for you to go all your life without ever knowing it. Because if it's one of those things where it's not a problem as long as you're sort of at low speed and you have no intention of ever being anywhere other than low speed, like you're not a physical person, you're not an active person or that sort of thing, it's possible that you could go all your life without ever really knowing it. It's not until you actually get to that point where you're trying to stress your body that you realize, okay, wait a minute, I can't do this. Why can't I do this? My heart should be able to do this for me, right? And then that's what sends you into it to get it checked out. So here is our key, right? So this is basically our heart. Now the best way to learn heart structure, by the way, absolutely use this when you're studying not just the models, but also the sheep heart, right? So when you're studying lab, absolutely use this. The best way to go through it is to basically follow the pathway of blood. So starting from the right to the left, basically you're going to have blood coming through the superior vena cava from the head and shoulders and from the brain, and then from the lower portion to the inferior vena cava from the trunk. So that's basically going to be coming in from the top and from the bottom. You also have this little guy right there. That's going to be that coronary sinus, which is coming in from the coronary system, so dumping blood in there. Ultimately, what's going to happen is this inlet of blood is going to fill up the right atrium. And then what's going to happen is the atria, both of them, right and left, are going to contract in unison. And as they contract, they're going to basically force the blood, that's what this arrow is doing, through the AV valve, in this case through the tricuspid. It's going to push open the flaps, the cusps that are associated with the valve. And then it's going to enter into the right ventricle. Now that's after, and of course, I'll talk about the left side here in just a second. I want to go through it in sequence in a linear fashion first. So then basically once it actually gets into the ventricle, now the atria relax. So they no longer have blood in them and they're constantly getting filled up again. So it's kind of starting to fill up. It's like a toilet. You think about it, if you've ever washed a toilet, you flush it, it's gone. And then the tank is filling up, right? And then you flush it and it's gone. And then the tank is filling up, right? So basically your heart is a toilet, right? So in this case, you flushed it. It all went into the bowl in this case, right? The ventricle, but it's constantly filling up. So it's refilling here and you're kind of waiting for it, so to kind of fill itself up. But while that's happening, it's time for the ventricles now to contract because they got to send the blood onto the next route. And so what happens is the ventricles contract, they're going to push the blood, and the blood's going to want to go where the blood's going to want to go. First of all, the blood's going to want to go backwards. That's one thing it's going to want to do. So it'll want to backflow. It's natural because there's a hole there. Why not, right? Well, that's a problem. So what happens is the way that the AV valves are arranged with the chordae tendineae attached to the papillary muscles prevents the blood from actually backflowing. As a matter of fact, what happens is when the blood pushes on this side of it, it shuts the AV valves. And then it can no longer go that way. So this basically prevents backflow the way that's set up. So the only other route you can go is forward through your first SL valve, which is going to be a pulmonary valve. So this is your pulmonary valve. So notice you have 3 half-moon cusps there. And so you're just going to push through and the blood's going to go into the pulmonary trunk. And then the first thing it's going to do, it's going to separate right and left pulmonary arteries. So here's your switch here from right and left pulmonary arteries. Those are going to go to the lungs. They're going to dump off waste and they're going to pick up oxygen. They've already got nutrients from the liver because it's already come from the inferior vena cava. They're going to pick up oxygen, dump off CO2, and then it's going to come back from the lungs, and it's going to enter through the pulmonary veins. And then from the pulmonary veins, you have both right and left, and there's another set behind that you can't see. That's going to fill blood in the left atrium. So now in the left atrium is oxygenated blood with nutrients in it. So it's charged up in both cases. And then you go through another cycle of atrial contraction. So the atria are going to contract. That's going to squeeze the blood through the mitral valve. Notice it's the same thing, right? You're going to squeeze it through there. The chordae tendineae that are attached to the papillary muscles will disallow blood from backflowing, because when the blood tries to, it actually shuts the valve closed. And then when the ventricle contracts, the left ventricle, in this particular case, it has only one way to go, which is forward through, you can see a little bit nib of it right there. That's the aortic valve. That's like a little half moon right there that you can kind of see in the aortic valve right there. So it basically goes through the aortic valve, and then it's going to go through the aorta, which is another great vessel. And there's an ascending portion of the aorta. That's the part that's going up. And then you go through the aortic arch. That's the sort of rounded area. And then you have the descending aorta, which is the part that's heading down for the rest of the body. Now it's off of the aortic arch that you get your three main branches in humans, right? So the first one that's coming off of that is your brachiocephalic trunk. The second one is your common carotid, in particular your left common carotid. So this will actually become a carotid artery. So your carotid artery is actually coming straight off of the aortic arch. So that's not too bad, right? And then the last one is going to be your left subclavian. So where does the right common carotid come from? Well, it splits off from the brachiocephalic, and you'll see that later on. But that's basically the direction of blood flow through the heart. A couple things to make a note of. First of all, the cycle of the cardiac contraction is that the atria contract first in unison, right and left, right? The right with the deoxygenated, uncharged blood that needs to be cleaned up and sent to the lungs. The left with the newly oxygenated blood that's cleaned up and ready for distribution. Both of them contract to their respective ventricles at the same time. And then after that, the two ventricles contract together. The right sending blood to the lungs, the left sending blood to the rest of the system. So it's atria, ventricles, atria, ventricles, atria, ventricles, like that. Boom, 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 boom. Right. The other thing also that always trips students up is that from the pulmonary trunk, the blood goes through, it's blue, right? So you can kind of see it's a bluish color. But they say it's like, oh, well, these are pulmonary veins, right? Because they're blue, right? All blue is veins. Well, that's mostly true, except when you're at the heart. The only thing that is true, regardless of where you are, is not the color, but the direction. If you're ever confused, always think of this. Arteries away, and you'll never go astray. So blood that's moving away from the heart is always arterial blood. Blood moving toward the heart is always venous blood. That's the reason why, even though it's blue and deoxygenated, it's not a vein. It's an artery. Why? Because it's going away from the heart. And that's the reason why these guys right here are not veins, even though they're coming toward the heart and they've got oxygen in them. These guys are not arteries, but they're veins, right? That's because these are going toward the heart. So rather than memorizing color, you can do that for the cat, right? Because in the peripheral system, which is what we're mostly focused on in the cat, that works. But when you're at the heart, it kind of gets flipped around that way, especially for the great vessels. So always remember that to keep yourself from getting too tied up. So this is actually what it looks like in a real heart. So we show that to you to show you that we're not lying to you. And we're not just drawing a bunch of pictures just for kicks and hoping that you're a bunch of suckers that will actually believe it. Okay. This is actually what it looks like. So, you can see, first of all, and you kind of saw this with your sheep too, right? In a lot of these images, like this one right here, it makes it look like the right and left ventricle are equally sized. Was that true? No, it's not even close, actually. The left ventricle is by far the dominant chamber. And in reality, I always like to say that the heart is a left ventricle world. Everybody else just lives in it. Not only that, but when usually you're talking about things, there's clearly a favorite here. The way your body's wired to speed this, there's clearly a favorite, and it's the left ventricle, which makes a lot of sense, right? I mean, does the right need to be very, very big? Not really. I mean, it's just pumping blood to the lungs. It's just right next door, right? However, the left ventricle, if that one screws up, you are toast, right? Because that blood is going to your brain. It's going to the rest of your body. So most of the blood in your body is coming off of your left ventricle. So really, if you think about it, your left ventricle is the primary pump. It's the primary chamber. The other three are sort of like in service to the left. Now, what does that mean? What that means is if you screw the left up, you are in some deep kimchi, right? I mean, that is like a serious, serious problem, right? Can you get away with screwing up the right? Yeah. I mean, you can't screw any of it up. Obviously, it's all important, right? But I mean, can you screw up the right and sort of survive that one a little bit? Yeah. What happens if you screw the left up? Not a lot of forgiveness there, right? Remember what we nicknamed the AI, the anterior interventricular, when we went over that in lab? What was the name of that one? Called it the Widowmaker, right? Why? Because the AI is actually is feeding. It's going right down the interventricular septum, the anterior interventricular artery, right? It's the interventricular septum, which feeds mostly the left side of your heart. We don't call the right marginal the Widowmaker. That's bad, right? But that's not the Widowmaker. I mean, the things like if you clog up or damage or compromise the function of the left ventricle, these are the things that you don't come back from, right? There's two ways you can survive a heart attack. Is if you get lucky on the severity front. If you're damaging your left ventricle, but it's not as severe or a very strong blockage or deprivation, then you got lucky. Or if it's in an area of the heart that's somewhat more permissive, like for instance, if you damage more the right side than the left side, that's another alternative to surviving a heart attack. The problem is, though, usually that damage, you have to end up living with it. Most heart patients, it is true that the clock is ticking, that they have met the thing that it will take them down. It's a matter of time. Now, they can push that out with good cardiology and staying close to their doctors and doing what they're supposed to and things like that. They can push that ultimate date with destiny out further, but that is what will come to get them, right? So that piece in there, and that's kind of part of the problem with the left is once you damage the left, there's no going back from that one, right? You basically are. It's a matter of time. Eventually, it's going to catch up to you, which is terrible. Which is one of the reasons why I left cardiology, because I got tired of getting to know patients and then having to watch them die, right? And then when they come in for the first time, knowing more than them, it's like, oh yeah, this is not going to go well. I mean, I'm glad you're happy and that it's going well right now, but the clock is ticking. Knowing that the clock is ticking, and it's like watching Walking Dead people. It's sometimes it gets a little depressing. Especially there's a lot of really nice people, because it's like there's something that's unique about a heart patient that's different than any other patient. It's like they come in and it's like they're beaming. It's like they've gotten a second lease on life. It's like they come in and they literally feel like, oh my gosh, I've just totally. I mean, it's like a radical life change sort of a thing. It's like they just completely realize that they've just gotten a new lease on life, and they fall in love with their doctor. I mean, they're like little groupies. I mean, they love their doctors because their doctors were the ones that saved them. It's like, yeah, this doctor, she saved me, so I'll do whatever she wants me to do. And there's a very strong bond in that sense. So, but anyway, there's that. So let's take a look at the right ventricle. So we already talked a little bit about chordae tendineae, right? So this is basically going to be the threads, if you will, of now notice what we're doing. We're going through the pathway of blood, aren't we? And we just talked about the right atrium. We talked about superior vena cava, inferior vena cava, coronary sinus. So now we're in the right atrium. And we basically now are moving through and going into the right ventricle. So this is the next step for the blood, the trajectory of the blood. So you have your tricuspid valve that's separating your right atrium from your right ventricle. And then, of course, you have your chordae tendineae attached to the papillary muscles on the inside of the right ventricle. And this is going to be stopping the backflow. So essentially, you only have a one-way route. Once you're in the ventricles, once the ventricles contract, then there's only one way to go, because you can't backflow because of this valve, right? The way it's tethered together will not allow you to do that. Matter of fact, if you look at it, think about it, I always like to think of a basketball hoop, right? So if we take obviously the basketball can go through the top of the hoop, through the net, right? We see that a lot, especially here in Denver, because we just won the championship. And so we saw a lot of that, which is a good thing, by the way. But you can also take a basketball, right? And you can throw it from underneath, can't you? And what happens when it hits the net? The net basically inverts, right? As the ball goes through it. Well, the same thing would happen with blood. If the blood went back through the AV valve, it would basically invert the chordae tendineae like basketball netting. And the blood would go right back into the atrium, right? So what that would give you then is a scenario where it's like 2 steps forward, 2 steps back, 2 steps forward, 2 steps back. It's not really helpful. It's not really useful, right? Because you're never going to be able to get that blood out to the tips of your toes. So what do? You basically hang on to the bottom, the papillary muscles. That's what they're doing. They hang on to the bottom of the net. So then what happens when the basketball goes up? What happens is it can't get through there because it's pushing the net closed, but it's not going to invert because the papillary muscles are hanging on to it. So the effect of the basketball is to slam it shut, but it can't get any further because the papillary muscles are keeping it from inverting. That means you only have one route. That's out. So one thing you'll also see on the inside wall of the ventricles is what's called trabeculae carnae. So this is kind of the ribs, these muscular ridges that are on the inside. How many of you guys saw that in the sheep muscle? Kind of the inside wall of the ventricle kind of looks like it's got these little ridges on it. That's trabeculae carnae. That's basically to increase surface area. Which is a way that you can get more productivity out of it without increasing volume. On the right side, you also have something that the left side does not have. You have a little strip of muscle that sort of crosses over the ventricle. So if you take a look at the right ventricle like this, the moderator band is basically it's like a little strip of muscle. How many of you guys saw that moderator band? It's like a little ribbon of muscle that connects the lateral wall with the ventricular septum. What this is supposed to do is it's supposed to increase and improve conduction. Which helps with communication and coordination. So, because it's a left ventricle dominated world, then the one thing that you want is basically your communication system is wrapped around your left ventricle, right? The right side is just sort of like left on the outside looking in. So one of the ways you communicate quickly with the right side is by short circuiting from the ventricular septum to the lateral wall, so that those lateral wall cells don't have to wait forever to get the signal. They can get it directly straight from the moderator band. So it improves and increases that uniformity of contraction to make sure that that right side lateral wall of the right ventricle is contracting at the same time. Because that way, because if it didn't, then what you would have is the left ventricle contracting, but the right side would be dead. And that would be a bad thing, because essentially you wouldn't be able to get that blood to your lungs to exchange it out for oxygen. This is a great image. I love this one. It's an endoscope view of an actual papillary muscle. So you can see the papillary muscle, actually, it does exist. They are real. And the chordae tendineae are actually also real as well. So you can see this little chordae tendineae is tethered to the papillary muscle that's hanging on to that AV valve, making sure that it doesn't invert when the blood tries to backflow on it. Love this image because you can also see some of the trabeculae carnae back in here, those ridges back in the background. So it's really, really good shot of the heart itself. Okay, where's the next step from the right ventricle? Well, it's going to the pulmonary trunk, yes? So that's the next stop. Let's take a look at that one. So once the ventricles contract, the blood is going to go into the pulmonary trunk. But at the bottom of, I guess you could think of the bottom of the pulmonary trunk or the top of the ventricle, it's kind of like a little swelling area called the conus arteriosus. So it's kind of like that little broad air shape. So if you looked on the previous slide, the previous image, the pulmonary trunk wasn't just straight. It kind of had this sort of like little, almost kind of inverted funnel shape to it. That would be the conus arteriosus. And I think they drew that here a little bit. So that'd be kind of like this area here, kind of fans out a little bit, sort of forms this like little upside down cone area right in there. It's kind of hard to see. You have to really look for it. It's not the kind of thing that would be like, okay, so this is going to be on the lab exam. It'd be more of like a surge tech sort of a thing, or a surgeon sort of a situation where you have to be able to find the conus arteriosus in order to be able to do surgery on this particular area, something like that. So then as soon as it enters in the pulmonary trunk, it's going to be dividing into right and left pulmonary arteries onto the way to the right and left lungs. And that's so they can pick up oxygen and drop off CO2. And on their way there, they go through the first of these SL valves that we saw, right, which is the pulmonary valve. We call them SL valves because we call them semi-lunar, so half moons is what it means. Pulmonary trunk is one, the aorta is the other. And what it has, both of these, by the way, are the same structure. Both SL valves are the same structure. Whereas the AV valves, one had 3, the other one had 2 cusps, right? We had tricuspid and bicuspid. This one, they're both the same. They have basically 3 of these half moon cusps. So if you take a look at them, they kind of form this. They kind of look like this, like 3 little half moons that come together like that. And when you see them on the outside, they're kind of like little sacs, like this. So you can easily go one way, but if you tried to come back, you can't do it because they're resting on each other. So it's like a one-way direct effect. So they basically will open up as you push through them, but when you kind of come down, you kind of snap them shut. Okay, so it's like a one-way system. So then from the lungs, you move to the left atrium, and you're moving from the left and the right pulmonary veins. Why? Because you're coming toward the heart in this particular case. You'll be dumping your blood into the left atrium. And then ultimately, at the bottom of the atrium is going to be your left AV valve, which is your bicuspid or your mitral valve. And so oftentimes you'll see mitral. For instance, there is a diagnosis called mitral valve prolapse, MVP. So it's actually a diagnostic term, the mitral valve is. And so you will hear some say bicuspid. I heard bicuspid maybe once or twice when I was working in cardiology. Most of what I heard was mitral valve. And as you could imagine, that on the left side, remember we said the left side is what dominates our attention. Then you would imagine that we are abundantly concerned if you have any kind of mitral valve dysfunction, because that's going to affect your left side, which is a killer, more so than the right side. So the left side everywhere gets more love than the right side, unfortunately. But that's because of its consequence. So that also extends up into the valve as well. We're much, much more concerned about the mitral valve than we are about the tricuspid. Okay. So then from the atrium, then it's going to contract and it's go into the ventricle. And so ultimately, the left ventricle has to hold all the volume that the right had, right? So you can't have less. You don't want an empty chamber, right? So basically, it's going to hold all the volume that the right had. It is, however, larger and more thicker. How many you guys saw this, right? When you saw the septum was like really thick. If you look at the lateral wall, the left ventricle versus the right, that wall is thick, as opposed to the right, which is like a little thin lateral wall, right? So you're talking about a lot of musculature. That means that a lot of your myocardium, the stuff that's contracting, is wrapped around and focused on the left ventricle. This is where we get to this idea that it's a left ventricle world. And we gear everything toward nursing the left ventricle. So because we wrap everything around the left ventricle, it doesn't need a moderator band because it's got all the great communication. It's already wired very, directly for maximum communication. It's only because the right side kind of gets left out in the dark that it needs that moderator band to kind of make things a little more efficient for itself. Okay. So then, once the ventricles fill, then it's time to contract them. So once we contract, then what we get is systemic circulation. Now, the first thing that's going to happen is as the left ventricle contracts, it's going to go through the aortic valve, right? So this is basically going to be the other SL valve. And then from there, it's going to go into the ascending aorta. It's going to go to the aortic arch. And then down to descending, right? So your aortic arch is this guy right here. Your ascending aorta is this guy right here. And your descending aorta is this guy right here. Then, of course, you have these branches that go off, your carotid, your brachiocephalic, and your left subclavian. And then, of course, from there, that's where we're into the CAT studies, the blood vessels, the CAT studies, where we're starting to move up into the thoracic cavity, and we're starting to learn all of those different arteries, names, brachiocephalic, subclavian, axillaries, things like that. And then, of course, the descending aorta, which in the thorax is the thoracic aorta, then will spit off arteries to the intercostals. It will then become the abdominal aorta, which will then spit off arteries to the digestive system, right? So we took a look at the celiac trunk, and then that gives way pretty quickly to the mesenteric, the superior mesenteric, and then the inferior mesenteric, and the renal arteries. So all those arteries are spitting off of that abdominal aorta as it goes down the back side of the wall until eventually it hits the iliac split, and it splits into both legs, and it becomes a femoral artery that goes down and feeds the legs. Okay. This is, by the way, just the exact same image as the first one. It's just kind of a bookend for you guys. So you can see here the thickness now of that interventricular septum, much thicker than the right-sided wall. So once you kind of get past the trabecular cornea, which is more like that right there. So much, much thicker, dominated by the left ventricle with kind of a little bit of a right ventricle kind of stuck on the side. So a couple of wrap ups between right and left. What's some differences? Obviously, the right is thinner. We talked about that one. The other big thing physiologically, we will talk about this a little bit, is there's less pressure there than the left. Why does that make sense? Doesn't need more. Why? Because the lungs are nearby. So you don't need to blast blood out of the right side because the lungs are just right there next door to you, right? However, the left, you have to blast it all the way out to the tips of your toes. So this has to come screaming out of the heart. And that creates some very significant structural and physiological realities that we have to account for. So the left ventricle is kind of like a round chamber, whereas the right ventricle is kind of more like a little side pouch on it. So this would be like left, this would be right. Now it's a little exaggerated, but that's pretty much what it's like. It's sort of stuck like a little pouch stuck on the side. Okay. So the heart valves we talked about, right? So you have two different pairs. You have the AV valves, which are separating your atria and your ventricles that have chordae tendineae that are attached to papillary muscles to prevent backflow of the blood itself. The other set of valves you have are the semilunar valves, right? So this is your pulmonary and your aortic valve. Both of them have three cusps, so they would technically be considered like tricuspids, although we don't call them that, so as not to confuse ourselves with the AV valve that's called the tricuspid. But these are the same thing, right? They're preventing backflow from the pulmonary trunk back into the right ventricle and also from the aorta into the left ventricle. And so they're kind of like a tripod. So a tripod basically has movement in one direction, but if you try to go the opposite direction, it doesn't move anymore. The other thing that we also want to cover, and there's a couple of images here that I want to take a look at, that'll help to sort of really visually drive this home. And I'm kind of moving that direction before we get there. We'll talk a little bit about the aortic sinus. So just like the conus arteriosus was at the base of the pulmonary trunk, at the base of the ascending aorta, another swelling area, kind of like that little cone-like area, is an area where you can kind of get pooling of blood near the ascending aorta at the sort of the first part of the aorta that gets blood. And so this is basically where your coronary arteries, both right and left, will come out of. And so in this particular area, you've kind of got these like little, they're kind of an appendage of the valve themselves. They're like little sacs that prevents the aorta from sticking to itself. But from this area, you're going to see the origin of the left and right coronary arteries, which is kind of important because a lot of times when we take a look at the coronary system, we will take a look at that system here in just a second. A lot of times it's confusing, right, as to where it's like, well, wait a minute, how do you actually get the blood off the aorta, right? I mean, if it's just screaming off the heart, kind of like water coming out of a fire hose, then how do you tap into that fire hose and sort of feed the heart without like really causing damage to the heart, because that's high pressure coming out of there, right? So that's kind of a problem. And so we'll take a look at that system and try to answer some of that a little bit. But this particular set of images I love because it's a cutaway. So you're looking, basically, it's a superior aspect of the heart cutaway, specifically designed to sort of look at the valves themselves. And so you can see the position of the valves relative to each other, and you can also see their structure, right? So for instance, in this particular situation, what you have is atrial contraction. How do I know that? Because the AV valves are open, right? That means there's blood going through those valves. You can clearly see what we mean by tricuspid and bicuspid, right? So here's the tricuspid. Here's 1, 2, 3 flaps of connective tissue. That's the tricuspid. In the bicuspid, we'll have 1, 2 flaps of tissue. So that's going to be the bicuspid. But the fact that both these are open means that right now, as it turns out, the atria are contracting, the blood is going through those valves and entering into the ventricle. And so you can see a couple of things. First of all, the structure of the AV valves is very clear, but you can also see at the time those AV valves are open, when the atria are contracting, notice the SL valves are closed. Why? Because it's ventricle contraction that opens those guys, and the ventricles aren't contracting right now. It's the atria that are contracting. But you can see here very clearly, you've got this nice, really strong ring of connective tissue with these very clear half moon cusps that basically form this kind of closed valve. And so this is actually what it looks like in real tissue, which is really cool because that's an actual real valve. And at this particular point, it's closed because you have atrial contraction. Now, this is kind of what's happening, right? So you can see that the atria are contracting, the blood is going through the AV valve, the SL valves are closed. So what's happening here? The blood in your aorta, which has pressure, is wanting to backflow. It wants to do that, but it can't. Why? Because when it sits on top of that aortic valve, it snaps it shut. It's very similar to the hatch of a submarine, right? I mean, I don't think we're in a submarine, but the hatch, you can basically open it up for the most part, right? Unless you've got the weight of the ocean on the other side. The weight of the ocean wanting to come into the sub holds the hatch shut. So even if you were to undo the hatch, you couldn't open it up if you were underneath the water because there's too much pressure pushing down on the hatch, closing it, right? That's the same thing that's happening here. So what's happening is the pressure of your systemic blood wanting to backflow because the ventricles aren't contracting right now is putting pressure on the aortic valve, snapping it together like a submarine hatch. So it can't even open up because the pressure is sitting on top of it. So if you were in here at this particular point, you'd be trapped because you couldn't open up that valve because you don't have enough force. Not that you'd be in there, but anyway, but if you were in there, right? So I'm thinking like Fantastic Voyage, an old classic. Go watch it. It's great. Yul Brynner. The dude gets killed by macrophages. It's cool, actually. But anyway, right? So you couldn't actually push with enough force on the inside of it to overcome that heavy weight of blood that's on the other side. Okay. But the important thing about that valve is it's designed to snap shut so that you don't get backflow coming back in. Just like the submarine hatch is designed to snap shut so that the ocean doesn't just come full flowing into the submarine, which is now a little more disturbing than not, considering that we now know what happened to that submersible. Which is one of the reasons why I have absolutely no intention whatsoever, ever in my life, of ever going that far underwater. I don't even like wading in the surf at the ocean because it's like nasty. It's like fish pee and poop all over the place, and people swim in that stuff. It's like a fish toilet. I mean, honestly, I'm not a big ocean person, but anyway. But well, I was from Sacramento, which means I was equidistant to the ocean and the mountains. So I chose the mountains. That's just the reason why I'm here. So Colorado was an easy choice. It was like a homing beacon for mountain people, right? So just like the oceans are a homing beacon for ocean people, which is great. They can have their ocean. I would rather not swim in fish sewage. And that's my most optimistic view of it. So that's as good as it gets. So now what happens is we're going to switch now to contraction of the ventricles. So notice what's going to happen is the blood's going to push against the AV valves, but the papillary muscles are going to hold it together. So you can see that I love this image, right? Because you can almost see how the blood is actually kind of forcing them to kind of snap shut. But they don't invert because they're being held on to by the papillary muscles. So that basically forces the blood through the semilunar valve, right, the aortic valve, and that opens up that aortic valve. So it's not gonna close it. So you have enough pressure that opens that up, and now you have flow through your aorta. And here's what it looks like. So now notice you can really see the cusps here on the AV valves. All right, so here's your 1, your 2, and your 3. Here's your 1 and your 2 and your bicuspid. Your AV valves are closed now, so preventing backflow, but the semilunar valves are opened up. So now the blood's coming out of the semilunar valves and heading either to the lungs or to the body, depending on which side you are. And you can see this is actually what an open aortic valve looks like. It's pretty cool. And if you get like a time lapse, you can actually see this happening. You actually see the valve going like, it's like really cool. You can actually see it. It's a nice image. A couple other things I want to point out though is notice that the valves, and it's oftentimes the question that comes up is like, well, wait a minute. So what about these valves? Are they just sort of like hanging out there in space and sort of like muscle space? I mean, we saw the toga, right? But you guys now know well enough from AMP1 that you don't just have muscle, do you? Muscle is always associated with what? Attachment, right? You have two attachments for muscle. What are they? Origin and insertion, right? Origin being the stationary point, insertion being the moving point, right? So in this case, it's also true. So origin and insertion. So your muscles have to be attached to something. So what are they attached to? You can't just have a blob of muscle, because if you have a blob of muscle with no attachments, it's basically, it's going to contract and it's going to be like quivering little blob, right? It's going to be like all up. I mean, it's not going to have any, rhyme or reason to it. And so what you are seeing here is actually the valves are an extension of what we call the cardiac skeleton. So this is basically a connective tissue skeleton that forms the valves and provides attachment for the myocardium. So your heart muscles aren't attached to bone. They're not originating on bone. They're not inserting on bone. They're basically attaching to this connective tissue cardiac skeleton. So it's a framework around which you're wrapping the toga. And then part of that framework, the extension of that, is the valves themselves. Okay. Which basically brings us to what the cardiac skeleton actually is. It's very simple. It's something that looks probably quite familiar to you if you were to take a look at it in AMP1. It's basically connective tissue. And so it's designed to support your cardiac muscle fibers, give them attachment. It also does another thing. It distributes forces, basically spreads it out. Spreads out the force of contraction so your contraction isn't localized or focal in any one area or point. So it spreads out that contraction. It also creates limitation. So you can't get overexpansion of the heart. Creates the structural boundaries around which the heart has to deal with. It's also elastic. It's basically malleable. To withstand the movement of the heart itself. So if you look at it, it's kind of crushable, right? So if you take a look at it, because connective tissue, it's elastic. And so it's got a little bit of crushability to it, right? So you can kind of squeeze on it and crush on it and distort it and it'll spring back to shape. That's kind of what elasticity is, right? So that's good, because what is your heart muscle doing? It's contracting, which means it's getting smaller, it's crushing down, right? And then when it expands, it's expanding outwards. So you want something that you can elastically crush down and then expand out and recoil. Crush down, recoil, crush down, recoil. So you need a connective tissue substrate that allows you to be able to do that. So ultimately, in your cardiac skeleton, you have 4 bands that basically form around the heart valves and forms the base of the pulmonary trunk and the aorta. So this makes a lot of sense, right? So this is basically your connective tissue support. So you don't just dump blood in there, you actually create a connective tissue or cardiac skeleton support system for that pulmonary trunk. So what are we talking about here? We're talking about the area of the aortic sinus and also the conus arteriosus, right? So that's going to be a very strongly supported area from this cardiac skeleton structure. And it also gives structure around the valves. So remember, there's blood going through these valves, which means there's a lot of pressure going through there, right? It's like a fire hose. You need to have something that can withstand pressure. And so this gives that valve structure, that valve system, a sense of stability. Notice what we mean by stability is that these valves aren't just winging it in space. They're tethered together. They're linked together. They're bonded together. So they're not just going to be sort of compromised or sort of moved or manipulated on their own. They're sort of tethered together and held together, bound together by this cardiac skeleton structure, by this connective tissue of the cardiac skeleton. And it can also create electrical insulation. And this will create conduction manipulation. By sealing off the conductive charge. And also by specifically routing it. So like the way that insulation on a wire basically focuses the flow of the charge down that wire, this kind of insulation activity of the cardiac skeleton can have a way of sort of focusing conduits of charge in particular directions in the heart itself, in particular, like from the atrial cells, right? Because a lot of times people will be like, well, wait a minute, how come, like, so if this is like an electrical thing, right, and all these muscle cells are contracting at the same time because they're hearing everything and all the myocardial cells are connected together, so how come both the atria and the ventricles don't all contract at the same time? Right? Because we just got done saying that they're all interconnected. So how come they're not all doing the same thing at the same time? Like all four chambers are contracting at the same time. Well, one of the reasons is because the cardiac skeleton insulates, puts a little barrier of insulation between the atria and the ventricles so that it can create specific conduits or pathways of charge that is a little bit more purposeful and a little more manipulated, as opposed to just having everything go at the same time. Right, so that's basically what they're talking about. Okay, so we are going to now shift to a slightly different idea here. We're going to be taking a look at the blood supply to the heart, right? Because the heart needs to eat too. So this is what we call the coronary circulation. So it's essentially you providing blood, fresh blood, to the tissue of your heart. And you do so by the coronary arteries and the cardiac veins. Those are the two that are involved there. And what I want to do is I want you guys to focus on, there's a lot, by the way, when you talk about the coronary system, there's a lot of little vessels and a lot of little things. So you could really get crazy with this. If you've ever seen like an angiogram of all the blood vessels of the heart, there's like a lot going on in there. So you can get crazy with this, but I don't want to. I want you guys to focus on just the things that we have outlined here. Starting first of all with the coronary arteries. So you have both a right and a left coronary artery, and you have branches, major branches that come off of each of these. Now, both of these guys are originating off of the aortic sinus. Here's the problem. The aortic sinus is like a fire hose. So what does that mean? That means you have to have a plan to take on that kind of pressure, right? And so this is going to be high pressure blood coming out of this. This is like front line. I mean, you're literally trying to drink right out of the nozzle of a fire hose. That's going to rip your lips off, right? So basically what you have is some elastic rebound associated with it. So what that means is that these coronary arteries have the ability to sort of rebound elastically. That means they have the ability to sort of take a punch. So when the high blood pressure comes in, they can sort of stretch to sort of mute and sort of dull down the blood pressure itself. And then what it'll do is it'll take in that blood and it'll start routing that to the heart itself. So let's take a look at some of the branches. So if you take a look at the right coronary, basically the right coronary's job is to supply blood to the right atrium and to portions of both ventricles, but most of the right side. This one is also famous for having the conduction cells that are associated with dictating your heartbeat. These are called the SA nodes, or the sinoatrial nodes. These are in the atrioventricular area. And so we'll see this a little bit when we talk about the conduction system of the heart itself. But the SA nodes are in the right atrium area, and the right coronary is the one that feeds those cells. So if you have a fundamental block in the right coronary artery, you're going to compromise your capacity to actually regulate your heart rate. It's something called arrhythmia, right? So when you have a dysregulation of your rhythm, that's arrhythmia. It will break into subsidiary branches. The two major ones that are important are the marginal arteries, right? The right marginal will actually feed the surface of the right ventricle. That's why it's an important one. It goes along the lateral side of the heart, skirting around the lateral wall of the right ventricle. That's the reason why it's feeding the right ventricle. And then the other one is called the posterior interventricular artery, right? That's the one that goes in the back, the anterior ventricular artery, but the right side does the posterior interventricular artery. So that's basically doing what it says. It's the posterior interventricular, or the interventricular septum, right? The posterior septum. So what about the left? So the left does a similar thing, only in this case, the left goes after the left ventricle. So already this means that it's the grand poobah, right? So the left is already more important than the right. It also will feed the left atrium as well, and the interventricular septum. Okay, so first of all, any one of those three, if you damage those, is bad news. So if you get a clot in the right, you get a little bit of arrhythmia, maybe some right ventricle dysfunction. If you block the left, you are screwed, because you cannot get past first base without these three in action. These three have to work in order to be able to be functional, like at any level from a cardiovascular means of things. So the left will turn into two major things. First of all, the first one is the circumflex. You guys saw this on your models, right? That was the small one that basically wraps around the underside of the left atrium and goes through the back. And then the other one is the anterior interventricular artery, right? This is the widowmaker. This is the one that feeds the anterior septum and the left ventricle. This is why it's the widowmaker, right? You block this one and you are all kinds of in trouble, right? So one of the things that I want to do is I just want to finish arterial anastomoses, and then we'll talk about the veins. We'll start off with the veins on Wednesday, right? So, because that's a lecture day. So we'll do the lab first, and then we'll do the lecture afterwards. But an arterial anastomosis, basically what this is, an interconnection between anterior and posterior arteries. So this is a connection. An anastomosis is basically a connection between two arteries. It's kind of like a portal system. Remember when we said you had to go all the way back to the heart in order to get back to another capillary bed, and a portal vein was a short circuit between two capillary beds connecting two. Well, this is kind of the same idea. It's a short circuit, only in this case, instead of capillary beds, it's arteries, right? Normally, like if you're in one artery and here's your other artery, you have to go all the way back to the heart and get pumped out again, and you have to go back to the other artery. So an anastomosis is basically like a shunt that connects these two arteries, okay? It's a cheat. It's a short circuit. This helps you to be able to move arterial blood around a little bit more efficiently, especially for the purpose of the heart, because you don't have to go through all that rigmarole, because this particular patch of blood, heart muscles needs blood quickly. So you want to deliver it there quickly. I've got it here, take it, right? We'll bend the rules here a little bit, but this basically helps to spread and stabilize the blood supply of the cardiac muscle, so you make sure that all the cardiac muscle cells are well fed. Okay. So it's just for purposes of efficiency. You don't usually do this. You only do this when you really need to, when you create these little short circuits. Okay. So we'll pick up with the veins that mirror these arteries, and we'll do that on Wednesday. Sound good? Since you guys are numb.